Hey everyone, Mr. Houck here. In today's video, we're going to talk about the basics of continuity through piecewise functions. Alright, let's go ahead and get started. So, this lesson is about piecewise functions and taking limits of piecewise functions, and the main theme of it is going to be continuity. So, the common sense definition of continuous is basically if you take a function and you trace the graph of the function over an interval without having to pick up your pencil, then we consider it continuous. So here's an example. Let's say our interval is from a to b. Here's our interval a to b. And if I were to trace the function from a to b, notice that I never lifted up my pencil, so to speak, my Apple Pencil in this case. However, let's consider this graph, and notice that we have a hole right here. We have an undefined value right here. Well, as I trace on this interval from a to b, notice that to go over this hole, I would have to pick up my pencil to continue. So this would be considered not continuous because the curve has a break in it. Okay, so this would be considered not continuous. This would be an example of a continuous function over the interval a to b. So that's kind of the common sense definition of continuity, of continuous. Now, mathematically speaking, a function is continuous at a point x equals a if the following are true. First, the function value f of a must exist. The right side limit as x approaches a and the left side limit as x approaches a must be equal to each other. And that means that the limit as x approaches a of the function must also be equal to the function value at a. And that kind of would guarantee you this kind of a situation right here. Okay? So let me repeat that one more time. The function value at a must exist, the limit of a must exist, and the limit and the function value must be equal to each other for a function to be continuous at a point x equals a. Okay? And here's how we would test that. First, we would test that the limit as x approaches a of f of x would exist. And you would test that by checking that the left limit and the right-sided limit exist and that they're equal to each other. That's how we know that the limit exists. Then we would check that the function value at a exists, and then we would check, finally, that the function value at a and the limit as x approaches a are both equal to each other. That's what this means right here. The numbers in test 1 and test 2 must agree. That means that the function value at a and the limit as x approaches a are the same number. Okay? So, let's look at some examples on a piecewise defined function. So here in example 1, this graph is our piecewise function, the graph of our piecewise function. We want to know at a few specific points if the function is continuous or discontinuous. So we're going to look first at x equals negative 4. So here's x equals negative 4. And one thing you can do is you can kind of, put a little line through negative 4 just to kind of help you visually with what you're doing here. But notice, as I would trace the graph from left to right, at negative 4, we have a break. I'd have to lift up my pencil to continue tracing. So here at negative 4, because it is not one smooth curve, since I have to pick up my pencil, it is not continuous. You can see this break from here to here. We call this a jump discontinuity. So at x equals negative 4, this is discontinuous. And specifically, the type of discontinuity is called a jump discontinuity. Okay, so we call that a jump discontinuity. Now let's look at x equals 0. So here at x equals 0, and again, I'm going to put maybe a little dotted line just to kind of visually see where I'm looking. So as I continue to trace and get closer to 0 on the x-axis, notice this hole right here at 0. So this hole, if I were to trace it, means I'd have to stop at the hole to jump over the hole and pick my pencil up to continue tracing the curve. So this is also discontinuous. However, this discontinuity, make sure I spell this right, this discontinuity, where you just have like a hole in the curve, like this, we call this a removable discontinuity. right? Removable discontinuity. Okay. All right, the last point we're going to look at is that x equals positive 2. And again, let me go ahead and just put a little dashed line to show us where we're looking. So we're looking right here. And notice as I trace the curve, well, it's just one smooth, continuous curve. I never have to lift up my pencil as I pass through x equals 2. So that part of the curve at x equals 2 is continuous. Okay, so hopefully you can see what we're talking about here with discontinuous versus continuous. And to kind of review them again, if we look here at x equals -4, as I trace the curve, I have to pick up my pencil to continue tracing the curve. So that was a jump discontinuity because there's a big gap right here. Then at x equals 0, as I trace the curve, we hit this hole. That means I have to lift up my pencil to jump over the hole to continue tracing the curve. So that's a removable discontinuity. But here at x equals 2, as I trace the curve, notice that I never have to pick the pencil up. I can just continue to trace the curve. So that's a continuous. It's continuous at x equals 2. All right. So with a graph, it's really not that hard to see. It's pretty simple, pretty straightforward. However, if we're looking at a function itself, the actual piecewise function, then we have to do a little bit more work. So in these next couple of examples, we're going to show you how you would figure out if we are continuous at a point, if we're only looking at the piecewise defined function. So here, for example 2, here's our piecewise function f of x. It says f of x is equal to 1 minus 3x plus 2x squared if x is strictly less than -2. So if x is less than -2, then x is to the left of -2. Okay? However, when x is greater than or equal to -2, then the function instead is 25 plus 3x minus x squared. So this is right of -2. And also equal to -2. Okay? So these are the two curves we're looking at. If the x values are to the left of -2, we would use this function. If the x values are to the right of -2 or equal to -2, we will use this function. So we want to figure out all of these limits right here, a through e. So first, we want to figure out the limit as x approaches -2 from the left. Well, left of -2, we would use that function. So we're going to take that 1 minus 3x plus 2x squared, and we're going to plug in -2. We're going to use direct substitution. Okay, so let's do that. So this will equal 1 minus 3x plus 2x squared, 1 minus 3, but instead of x, we're going to directly substitute x with -2. So 1 minus 3 times -2 plus 2x squared, so plus 2 times -2 squared. And let's simplify that. -3 times -2, that's positive 6. So 1 plus 6. And then here, -2 squared, we do the exponents first. So -2 to the second power, that's -2 times -2, that's 4. And then 4 times 2 is 8. And then 1 plus 6 plus 8 is 15. So we can see that to the left of -2, the limit is 15, whereas we approach -2 from the left. Now let's take the limit as x approaches -2 from the right side. So to the right of -2, we'd have to use this function, 25 plus 3x minus x squared. So 25 minus 3, and then x we're going to replace with -2, minus x squared, minus -2 squared. All right, let's do some simplifying. Again, -3 times -2, that is going to be, wait, did I copy that down wrong? Yeah, I copied that down wrong. It should be a plus 3x. So easy fix, that should be a plus 3 times -2. So my bad on that one. So 3 times -2, that's -6. 25 minus 6. let's see, negative 2 squared would be positive 4, and then we're subtracting it, so minus 4. And let's see here, 25 minus 6, that's going to be 19. 19 minus 4, that's going to be 15. So notice that the limit as x approaches negative 2 from the left was 15. The limit as x approaches negative 2 from the right is 15. If the left and the right-sided limits as x approaches negative 2 are equal to each other, then the limit as x approaches negative 2 is going to be equal to 15. Nice and easy. Okay, so let's try this one right here. The limit as x approaches negative 3 of f of x. Well, if we think about negative 3, remember that the piecewise defined function says that anytime x is less than negative 2, this is what we're going to use. Well, if x is negative 3, or if x is approaching negative 3 is to the left of negative 2. So we're going to use 1 minus 3x plus 2x squared. All right, so I'm taking the negative 3, and I'm just directly substituting it into this part of the piecewise function, which is defined anytime x is less than negative 2. Okay, and let's go ahead and simplify. So negative 3 times negative 3, that's going to be 9. 1 plus 9. Negative 3 squared, negative 3 times negative 3, that's 9. And 9 times 2 is 18. And if we simplify that, 1 plus 9 plus 18, that's equal to 28. Right. Next, our last one for this example, let's calculate the limit of f of x as x approaches negative 1. So x is now approaching negative 1. Well, for this piecewise defined function, negative 1 is to the right of negative 2 on the number line. And, think about this as the number line, right? Here's negative 2. We can see that negative 1 is to the right of negative 2. So we're going to use this part of the piecewise function, 25 plus 3x minus x squared, and let's directly substitute in negative 1 for x. So we have 25, make sure I copy this down right, plus 3x minus x squared, so plus 3 times negative 1 minus negative 1 squared. Okay, and let's simplify. 3 times negative 1, that's minus 3, so 25 minus 3. Negative 1 squared is positive 1, and then we subtract it, so minus 1. And if we simplify that, 25 minus 3 minus 1, that's going to be 21. Okay, nice and easy. So let's try that one more time here with example 3, and this time we'll move a little bit faster here. So here in example 3, here's our piecewise defined function. We can see that f of x is going to be 3 plus 2x plus x squared anytime x is less than 2. So what this is really saying, if x is less than 2, this is left of 2. And if x is greater than or equal to 2, this is right of 2 or equal to 2. Okay, so we want to find the limit as x approaches 2 from the left. Well, left of 2, we'll use this function, 3 plus 2x plus x squared. So 3 plus 2 times 2 plus 2 squared. So we're directly substituting 2 into the left side function. If we simplify, that's going to be 4, that's going to be 4. So we have 3 plus 4 plus 4, which is 11. Okay. Now, let's calculate the limit of f of x as x approaches 2 from the right side. Well, right of 2, we will use this function, 6 plus 2x plus x squared. And again, I'm going to go ahead and directly substitute 2 for the x's. Okay, so calculating here, That's going to be 4, that's going to be 4, so that'll be 6 plus 4 plus 4, which is 14. So now let's think about this. As x approaches 2 from the left, the limit was 11. As x approaches 2 from the right, the limit is 14. And this is for 2, right? 2 from the left, 2 from the right. So this means that the left-sided limit and the right-sided limit are not equal to each other. And if the left-sided limit and the right-sided limit are not equal to each other, then the limit, as x approaches 2, of this function does not exist. Okay, again, left and right side limits don't match each other. One last little problem here in this example. Let's calculate the limit of f of x as x approaches 3. So x is approaching 3. 3 is to the right of 2 on the number line. So we would use this function, 6 plus 2x plus x squared. 6 plus 2, place the x's with 3's. And let's see here. 2 times 3, that's 6. 3 squared, that's 9. So 6 plus 9. And let's see, 6 plus 6, that's 12. 12 plus 9, that's 21. Okay, so that's how these piecewise defined functions work. Let's do one quick little recap, and then we'll wrap this video up. So just to recap this video, the common sense definition of continuous is that if you can, on an interval from A to B, or whatever interval you're given, if you don't have to pick up your pencil to trace the curve, it's continuous. If you do have to pick up your pencil, such as right here where we have to jump over this hole, then your function's not continuous on this interval. Mathematically speaking, these are the conditions you must meet for a function to be continuous. The function value at a must exist. The limit as x approaches a must exist. And the limit as x approaches a must equal the function value at a. There are a few types of discontinuities. One of them would be a jump discontinuity, which you can see right here. If I were to trace, we can see this jump that happened, where we had to pick up our pencil as we trace the curve. That's a jump discontinuity. You can have a removable discontinuity, which is basically just a hole. So example here was at x equals 0. We see this hole right here. So to trace the curve, we'd have to jump over the hole. That's a removable discontinuity. There's also a third type of discontinuity that wasn't mentioned here in these notes, and that's called an infinite discontinuity. An example of an infinite discontinuity would be right here at x equals 1 from the right side. Notice as I approach 1 from the right, the function values are blowing up towards positive infinity. We would call this an infinite discontinuity here at x equals 1, because there's an infinite amount of space between those. Okay? And then finally, if we're trying to find the limit with piecewise defined functions, we just need to identify what is the left side of a certain value, the right side of a certain value. And when you're trying to take limits, you just want to keep in mind, am I to the left of that x value, or am I to the right of that x value? And then you can go ahead and plug into the appropriate part of the piecewise function to get your values.